let's look at what's happening inside the filter at the level of the pores. So what I've drawn here is 3 sand grains, which for some reason turned out to be green. Don't ask me why they turned out to be green. And these 3 sand grains form a pore. The pore is this narrow constriction in between the 3 sand grains. And that constriction, that pore, slowly fills up, but not completely, with particles and flocks that are coming in from the clarifier. And that constriction in the middle keeps on getting smaller and smaller until when a flock tries to enter that constriction, the force of drag on that flock is larger than the coagulant nanoparticle chemical bonds can withstand. And so even though the flock attempts to attach to the side of that constriction, it can't because it's being pushed too hard by the water. And so it keeps on going through. Do you see how this is such an important piece of understanding what's going on inside filters? The filters allow even the biggest flocks to just go right through the filter at the end. When the filter is full, when all these constrictions are made, flocks just go right through because the viscosity is dragging those particles right through the filter. So now you know why even a full filter can easily transport flocks from the influent to the effluent and have them pop right out the bottom. They just go sliding right through all those pores because the force of drag is greater than the bond strength that those coagulants, that those flocks might have trying to attach to the wall of the constriction. Here's another interesting insight. The head loss in the filter, this is the pressure drop or the change in water level between the water going into the filter and where it comes out of the filter, is close to linear before breakthrough. So remember, breakthrough is when flocks start coming out the bottom. So here's the first one for 1.5 milligrams per liter. That green dot marks when breakthrough began happening. And you can see that although your eye tells you that the green curve is clearly a curve and that it bends over, if you look at the place where it is not yet having broken through, when breakthrough hasn't yet happened, that part of the curve is actually a straight line. Like you're hard pressed to see any curvature in that part of the line. Here's another one. Same thing, like there's really no evidence of curvature in the first part of that yellow line until after breakthrough happens, and then we begin to see curvature. So I don't know if this strikes you as odd, but here we have this complicated system where we have sand getting somehow filled up with some flocks, and yet the pressure drop through that sand column just increases nicely, linearly with time. Does that seem surprising to you? Like, think about how complicated this is. Like in the previous slide, I showed you this, constrictions getting smaller and smaller. That process of constrictions getting smaller and smaller has a very non-linear effect on head loss, right? As this constriction is getting smaller, head loss is like super rapidly ramping up because the velocity going through that pore, that hole, is increasing fast, and the head loss goes with the square of the velocity. So that is a very nonlinear process. And yet here we get this linear head loss with time. So anyone hazard a guess what makes the head loss or the pressure drop through the filter increase linearly with time? Anyone? Or, or tell me, does this seem surprising to you? Like if I had, maybe I should have done this first. Like if I had asked you to predict what head loss will look like in a filter that is filling up with particles, what would you have guessed would happen? Yeah, like I would have guessed that it would increase slowly at first and then it would ramp up and go up really fast. Yeah, but that's not what happens. It's linear. It's beautiful when it's linear, and it means this is data that is begging us to figure it out, right? There's something happening here that's interesting. So here's what I think is happening. So head loss is directly related to what fraction of the filter is already full, meaning that the pore constrictions in that part of the filter are already as small as they're going to get. So remember, here's the idea. Each pore is slowly loading with particles and gets as small as it can possibly get until the velocity inside that pore is so fast that no more particles can attach. At that point, all the particles that come up to that pore just blow right through and keep on going deeper into the filter. So that means that the number of pores that you have to go through to get to a pore that's open and ready for more particles to be deposited is a function of how much dirt has been, or flocks have been deposited in the filter thus far. So maybe it takes, let's say it takes a minute for one of those pores to fill up. Then in 2 minutes, 2 of those pores are filled up. And in 3 minutes, 3 of those pores are filled up. And as you're coming down through the filter, by the time you get to 5 minutes, you've got to go through 5 of those clogged pores, and you've got the head loss of 5 of those pores to deal with. Did that make sense? So head loss increases linearly with time because the number of formed and fully constricted pores is increasing linearly with time. Then at the end, after breakthrough has happened, head loss continues to increase. And it continues to increase some more, but it increases more slowly. And I'm at more of a loss as to what's happening here. Maybe the pores are continuing to constrict a little bit more. Maybe some small particles are able to deposit on the inside of a pore. Maybe a big particle can't constrict because it just gets pushed through by the force of the water. But maybe a small particle can attach to the side because it's experiencing less shear. So maybe the pores do continue to constrict a little bit, or the flocks that make the constrictions are becoming less porous. So now I'm reconnecting this to what we think we understand about what's happening inside flock filters. Remember, in flock filters, some of the water is flowing right through the flock. And the flock is slowly becoming less porous because particles are being captured inside that flock. So maybe the same thing is happening here. Do I have a video of this? No, I have an animation at some point soon about this. Here's another insight from these graphs. Breakthrough happens sooner with higher coagulant dose. So why does the increased coagulant dose result in earlier failure? Why does more coagulant make it not last as long? So here's the hypothesis. If you add more coagulant, then there was a flocculator before this filter. And that flocculator was a relatively small G theta, relatively little deformation of the fluid. As we increase the coagulant dose, we increase what fraction of the clay particles are coated with coagulant and how much sticky surface there is on each clay particle. That means that when two clay particles attach, if the coagulant dose is higher, the probability that those two particles attach is higher, right? If you increase the coagulant dose, then the chances that you hit sticky when you come together is greater. And so the flocks inside in the flocculator are going to grow faster and larger when we add more coagulant. So it's possible, because we didn't have any clarifier in this system, that we produced bigger flocks when we added the coagulant, more coagulant, and those bigger flocks occupy more volume. And this is because they're fractals. Remember, flocks are fractals. So if the amount of water that's part of the flock increases as it increases in size, and so these bigger flocks effectively occupy more volume. Why is the head loss accumulation faster when we have more coagulant? I'm actually less sure on that one. This still needs some more model development to figure that one out.